The first thing we're going to do is assign the material that we created to our part. So click on the blade FEA part, and under assignment, change the material to homogenized orthotropic. Now we need to create a new coordinate system, and I'll explain why we're doing this soon. So right click on coordinate system, insert a coordinate system. Define it by the global coordinate system, and leave these values as zeros, so that this new coordinate system is really just a copy of the global coordinate system. Now back in our part, change the coordinate system to the one that we just created. We created this new coordinate system because global coordinate system is not one of the options here. So basically, when we specify the coordinate system for the blade to use this coordinate system, it's going to map the x direction onto the element face, and that's going to be our reference direction for our material axes. So it's going to take this x-axis and basically project onto the face of all the elements so that our x-axis is consistent. This is important because we're using shell elements. If we forget to do this, then our material x-axis is aligned with our element ij connectivity, and we have basically an orthotropic material that is infinitely variable in its orientation. Alright, so next we will define the thickness of our blade. So if we expand our part here, do you notice these question marks? This means that mechanical is lacking some information before it can solve our solution. If we click on one of them, it looks like we need to input a thickness for each of these surface bodies. From the problem statement, we're told that the thickness varies linearly, so you might wonder what we should do here. Well, there's actually an option to insert a thickness if you right-click on geometry. This is actually going to be the way that we will define our linearly varying thickness. It will actually override any thickness that we input here for these surface bodies, which means that we can just put a dummy thickness for these. So highlight all of them, and then input a value, say 0.001. Again, this thickness will not be used because it will be overridden by the thickness that we will now define. We will start with the blade surface. So change the scoping method to name selection and choose the blade surface. Instead of only giving one thickness for this whole blade, we can actually click on this arrow to have more options. We're going to click on Tabular, and to see this table you need to click on the Tabular tab, and we're going to drag this up a bit. Now we can input the thickness at the root and at the blade tip. So the values that I will input are from the problem statement. Be careful because the order of these points might change on you due to the -x direction. So notice this nice visual to see the thickness. Also, we can click graph here. And it will also show the thickness. And so what it really just did is it linearly interpolated thickness to all other locations on the blade. We're now going to give the spar thickness as well, and the process will actually be the same as what we just did. a really neat way to see this thickness is to look back at the mesh. So if fixed shells and beams is selected here in the view menu, then ANSYS will display the relative thickness of the shell elements.